roughly 311 miles, about 500 kilometers west of Oregon's shoreline, far below the gray swells of the Pacific. A hidden volcano rises from the abyssal plain. This undersea mountain, called Axial Seamount, sits squarely along the fiery backbone of the Pacific Ring of Fire, the vast horseshoe of faults and volcanoes that girdles the ocean. The Pacific Northwest is no stranger to restless geology. It is home to the Cascades and to infamous peaks like Mount St. Helens, whose 1980 blast still serves as a cautionary tale. The story stretches back millions of years to when the Pacific Plate began diving beneath North America. That slow-motion collision helped build the Cascade Arc from Northern California into British Columbia, and it also set the stage for submarine giants like Axial. From the seafloor, it climbs like a dark cathedral, its summit still roughly 5,249 feet, about 1,600 meters, beneath the sea surface. Lately, something unusual has been stirring down there. In a single day, instruments recorded more than 300 earthquakes around Axial, a spasm of motion that is far from routine. The pattern of shaking has scientists on high alert because it resembles the run-up to the seamount's previous eruptive episodes. One veteran oceanographer put the risk in stark terms. If this were happening beneath a town rather than beneath thousands of feet of water, emergency managers would already be clearing neighborhoods and putting evacuation plans into motion. The Pacific may look calm from a ferry deck. The forces below are anything but. So what's driving this drumbeat of quakes? The best explanation points to magma creeping upward through fractures in the oceanic crust. As molten rock pushes into the plumbing system beneath the summit, it pressurizes the volcanic edifice. Think of a balloon being slowly inflated inside a rigid box. At some point, the pressure has to find release. When that moment comes, the seafloor can split, lava can pour out, and the volcano can undergo an eruption, measured not in towering ash plumes, but in rivers of basalt that harden into black glass on contact with cold seawater. The year 2025 has already delivered several eyebrow-raising bursts of activity. In June, instruments tallied an astonishing flurry, more than 2,000 earthquakes in just 24 hours. That spike eventually eased, settling back to roughly 100 tremors per day for a time, but counts have again climbed into the hundreds. Even without any one massive jolt, the sheer persistence of these tiny quakes is a red flag. To grasp the scale, remember what happened the last time Axial really let loose. During the April 2015 event, over 8,000 earthquakes were logged in a single day. That is the tempo of a volcano in full swing. Today's numbers are lower, but the trend line and the style of the signals echo that run-up. And that is why researchers are treating the present sequence as more than a curiosity. A second, equally troubling clue is showing up in the shape of the volcano itself. Axial appears to be inflating, its surface subtly lifting as new magma collects in a reservoir beneath the summit. Before the 2015 eruption, that ballooning reached a notable threshold, and measurements now suggest the edifice has swelled back to similar levels. The tempo of uplift has accelerated too. Whereas typical years saw the ground rise on the order of 2 to 4 inches, roughly 5 to 10 centimeters, the rate jumped dramatically beginning in January 2024. By July, some stations near the center of the caldera had captured as much as 6 inches, about 15 centimeters, of cumulative uplift, and peak pockets were pushing toward 10 inches, around 25 centimeters. That's a remarkable amount of motion for rock to undergo in such a short interval, and it fits uncomfortably well with the surge in microquakes. Both are classic symptoms of a magmatic system under pressure. All of this is unfolding inside a volcano with serious dimensions. Axial is not a neat cone. It's a sprawling complex capped by a caldera and rift zones that stretch for miles along the seafloor. The main magma storage zone sits around 2,625 feet, about 800 meters, beneath the top of the edifice, a sizable chamber of molten rock feeding the system. Although its summit remains more than 1,000 meters below the ocean's surface, which muffles direct effects on coastal communities, there is nothing small about the forces at work. For volcanologists, Axial is both a laboratory and a test. Here's a system we can watch closely, one that erupts often enough to study modern processes in real time, and one that can teach us about the rhythms of more dangerous volcanoes on land. Predicting eruptions is notoriously difficult, but Axial may be giving scientists the best shot yet at a well-timed forecast. The volcano has a quirky personality. Periods of rapid inflation can be followed by quiet plateaus, then by renewed surges. But the current combination of inflation, seismicity, and the sheer pace of change has led some researchers to a striking conclusion. Odds favor an eruption before the end of 2025, possibly at any time. That doesn't mean a cataclysm is guaranteed, and the ocean will absorb much of the spectacle. Yet from a scientific standpoint, capturing such an event with modern eyes could be historic. That's because the monitoring toolkit on site is far better now than in previous cycles. A sophisticated network of cables, junction boxes, and sensors sits on and around the caldera, streaming data continuously. Tilt meters watch the ground breathe. Pressure gauges register tiny changes in the overlying water column. Seismometers listen for the crackle of moving magma and the pop of breaking rock. Some nodes are tied into cameras and chemical sensors, ready to catch visual signs, plumes of shimmering water, sudden turbidity, or hydrothermal fluid bursts, should the seafloor split. Instead of occasional research cruises, stitching together snapshots weeks or months apart, scientists now have a live feed from the deep, second by second. If Axial opens a new fissure, that system could record the sequence with a level of detail never achieved for a submarine eruption. The earthquakes being tallied are not large in the way the public imagines earthquakes. Most cluster around magnitude 1 to 2. But in a volcanic setting, that's exactly what you'd expect. Swarms of small events that collectively map the path of magma as it wedges itself into cracks. Each tiny quake is a stress whisper, a brittle fracture here, a slip there, a local pressure drop, followed by renewed push. The pattern matters more than any single number. A broadening swarm, increasing rates, a change in the dominant depths. These are the signatures forecasters watch, and recently those signatures have been trending in the direction of unrest. It's worth emphasizing that undersea eruptions differ profoundly from those on land. There will be no ash cloud blotting out the sun, no red fountain visible from coastal highways. The pressure of 1,000 meters of seawater forces lava to quench instantly into jagged pillow shapes, piling up like toothpaste squeezed into ice water. Still, the consequences can be significant. New lava can dam or reroute hydrothermal circulation, altering ecosystems. Seafloor topography can change over days. In some cases, gas release or rapid heating can drive local hazards at the surface, though at Axial's depth, the ocean generally dampens such effects. For ships and nearby infrastructure, the main risks would be to subsea floor cables and instruments, not to ports and cities. Even so, studying Axial is not an academic luxury. The physics of magma moving through rock are universal. Lessons learned here: inflation thresholds, the relationship between seismic swarms and dike intrusions, the way pressure migrates through a branching rift network, translate to stratovolcanoes that do loom over towns and highways. Every data point from Axial sharpens our playbook for hazards on land. If researchers can validate a reliable chain of precursors at this seamount and peg the timing of an eruption within a meaningful window, it would represent a milestone for eruption forecasting writ large. None of this erases the reality that volcanoes can faint. Axial's history includes stretches of rapid uplift that stall, intervals where quakes scatter then regroup, and episodes where magma intrudes along a rift without breaking the surface. Forecasts must dance with uncertainty, but uncertainty is not ignorance, and it is not paralysis. It is a quantified range, narrowed by each new sensor, each fresh data set, each additional hour of continuous monitoring. Right now, the picture looks like this. The volcano has reinflated to levels comparable to those seen before the 2015 eruption. The rate of inflation accelerated markedly, beginning in early 2024. Earthquake counts surge to extraordinary highs in June 2025 and continue at elevated levels measured in the hundreds per day, and the overall behavior suggests a pressurized system. The simplest interpretation is that magma is on the move and that the system is trending toward a release. If and when that release happens, the sequence is likely to unfold rapidly. A dike, a blade-like body of magma, could propagate along one of Axial's rift zones, opening a fissure on the seafloor. Seismicity would spike, then reorganize into a migrating front as the intrusion advances. Tilt meters might register sudden steps. Pressure sensors could show subtle changes as warm fluids pulse outward. Cameras, if lucky enough to be pointed in the right direction, might catch the water clouding and shimmering. Lava would extrude and cool into lobate pillows, building new crust, even as the underlying reservoir deflates and the ground above sags. After days to weeks, the system would quiet, leaving behind a freshly minted patch of ocean floor and a trove of measurements for scientists to decode. For now, the best course is vigilance. The deep ocean network continues to hum, logging every tremor, every millimeter of rise or fall. Research vessels stand ready to sail when weather windows open. To ground truth, the signals with plume sampling and high-resolution mapping. And the public, though insulated by distance and depth, can take real comfort in the fact that this is a volcano we can watch in detail, one whose behavior is teaching us how to read the signs at other, more immediately consequential volcanoes around the world. Curiosity about Earth's hidden machinery is more than a hobby. It's a form of preparedness. The more we understand how magma moves, how rock responds, and how seafloor systems breathe, the better we can anticipate the next chapter, underwater at Axial, or atop a mountain closer to home. If this kind of deep time detective work fascinates you, stay tuned. We'll keep translating the pulses of the planet into stories you can see and understand, as this undersea giant writes its next line in the Pacific's long volcanic script.